Alright, today we have two questions, two samples to go over. We've got a pressure or gravity example and we've got a hydrostatic force example. So here we have our pressure and gravity example. We've got a manometer, which is a device for measuring pressure differences. It's filled with water, and we can see there is a height difference between the levels of water on the left and right hand side. On the left hand side we've connected our manometer to some vessel having pressure PE, and on the right hand side we've got the tube open to atmosphere, which has a pressure of 100 kPa. If the height difference is 200 millimeters, then what is PE? Well, it's quite a simple problem really. We need to find a way of defining what the pressure P is at the center of the pipe, where I've got a dot there, you can see the P. If we tried to compute what that pressure was, approaching the problem from the left hand side, we can see that the pressure should be PE, which is what's in the tank, plus the hydrostatic pressure, which is rho GH1. That gives us a formula for P. Now that P is going to be the same as P on the right hand side, which is PO, atmospheric pressure, plus rho G times delta H plus H1, where delta H is the height difference between the left and right hand sides. Some of those terms are going to cancel, so we end up getting an equation saying PE equals PO plus rho GGH. We can cancel some terms there, or sorry, we don't cancel any terms there, we just compute those out. PO is 100 kPa, rho for water is about 100 kilograms per meters cubed, and G is about 9.81. Take care of the units here. Our delta H is 200 millimeters, which is 0.2 meters, and that gives us that pressure there. And now we're on to our hydrostatic force example. In this problem we have a triangular plate submerged underwater. We want to know what the total force due to water pressure is on one side of that plate. To do this we need to compute pressure as a function of some depth. To do this we introduce a variable x, which measures the distance from the top of the plate downwards, and we can see that the pressure is going to be a function of that x. The rho g times 9 is going to be the pressure at the top of the plate, and rho g 9 times plus x is going to give us a pressure at any point along that plate. If we want to work out what the force is, we need to integrate that pressure along the plate by element dA. What is dA? dA is going to be the elemental area size as we're going down in the distance x along that plate. We know that our plate is triangular in size, so as we increase our value of x, our area is going to increase because it gets longer. Initially, it has length 0, it finishes with length 6. So we can say that the relationship between the length of that strip dA is 2x with regard to x. That gives us an equation for dA of 2x dx. Now we can substitute that dA into our original equation. So we can see that our integral for pressure, or integral for force, integral from 0 to 3, because our plate is 3 meters high. We've got rho g 9 plus x, that's P, and then we've got dA, which is 2x dx. We can take some things out because rho and g are constant with regards to x, that's not going to change. And then we perform our integral. Integral is pretty straightforward, and we can see that our result will be 99 times rho g. There are other ways, easier ways to compute what this force is. I'm going to leave those to you. If you need more help, you can come see me anytime in room 714. You can email me at that email shown on the screen. If you'd like some clues about the easier way to solve that hydrostatic force, come and see me. Good luck, and I'll see you next class.